dear students. I'm Dr. Neelam Yadav from ABES Engineering College. I'm preparing this lecture video on the topic Graphite and Fullerene. The contents which I'll be covering in this lecture video are structure, preparation, properties, and applications of two allotropes of carbon. One is graphite and the other one is fullerene. The basic structure of graphite is given in this picture, and viewing its physical state, it looks like a lustrous substance and it is made up of pure carbon atoms. Now discussing the structure of the graphite. Graphite is having a two-dimensional planar sheet-like structure which is formed by the combination of carbon atoms in the form of hexagons, and these hexagons are formed by the covalent bonds. The various hexagons are joined together and they form a sheet-like structure, and this sheet-like structure is called as graphene. Each graphene is arranged one above the other, and the distance between the two graphene sheets is 3.41 angstrom. These sheets are also attracted to each other by weak van der Waals forces of attraction. Further, the carbon atoms which forms the hexagons are sp2 hybridized. This can be viewed from the diagram over here. When the carbon atom is in its ground state, it is having a configuration of 1s2, 2s2, and 2p2. When this carbon atom is brought to the excited state, one of the electron from 2s orbital jumps into the p orbital, and now due to the hybridization, the sp2 hybridization is formed, and the carbon atom is having a trigonal planar structure in the graphite, while one of the p orbital is having a single electron, and this single electron is responsible for the electrical conductivity of the graphite. Again, the carbon-carbon bond length formed is having a distance of 1.42 angstrom. This is the view, or this is the structure of the graphite, which is having graphene sheets, which are at a distance of, here it is given in nanometers. So nanometer distance for two different graphene sheet is 0.34 nanometer, or it can be also said as 3.41 angstrom, while the carbon-carbon bond length shown here is in nanometer, it is 0.14 nanometer, or it can also be called as 1.41 angstrom. Each carbon atom is having three covalent bonds, and the fourth electron is free, which is helping in the electrical conductivity property of the graphite. Now, preparation of graphite. This graphite was prepared accidentally by Edward G. Axon while he was working on high temperature experiment on carborundum. At a temperature of 4150 degrees centigrade, he left the carborundum during unattended, and in that case the silicon vaporized, and the carbon received after that was having the structure which is very much resembling to the graphite. So this is the way the graphite was formed and derived. Now to discuss the properties of the graphite. It is a black and greasy substance. It is having a luster like a metal, but it is not a metal. It is opaque in light. It is having a high melting point due to strong covalent bond present between the carbon atoms. It is having slippery nature, or the layers can glide over each other due to the presence of weak van der Waals forces of attraction between the two layers. Now, the electrical conductivity which the graphite is having is due to the presence of free electron in the pz orbital, which we have already discussed in the sp2 hybridized concept, which was discussed in the structure of the graphite. This free electron present in the pz orbital can easily move through the structure and help in the conductivity of this graphite. Most of the time, graphite exists in two basic forms, alpha graphite and beta graphite. Here, the difference between the two is that the alpha graphite is having the basic structure of AB form, like first layer is starting from one position and the second layer is starting from another position, and then the third layer will start from exactly the position where the first layer exists. Similarly, for beta graphite, the structure is as first layer starts from the position 1, second layer starts from position 2, third layer starts from position 3, and then the fourth layer starts from the position 1. So the arrangement of the layers in different ways results in the formation of alpha graphite and beta graphite. Again, the graphite is very stable thermodynamically and often more stable than diamond. Graphite also shows low coefficient of friction. It is also ineffective in vacuum conditions. The density of graphite is 1.25 gram per centimeter cube. Now, this graphite, depending upon its property, it is having various applications. Like due to its slippery nature, it is used as a lubricant, and the reason being the weak van der Waals force of attraction between the layers. It is also used in pencil leads, and this is also due to the presence of weak van der Waals force of attraction between the layers. So when the pencil lead is glided over the page, it leaves the mark due to its slippery nature. Again, graphite can be used in the preparation of electrodes as it conducts electricity due to the presence of free electrons on each carbon atom. Graphite is having a high melting point and it is used for the preparation of crucible, which is used for making a high-grade steel. Graphite is also used as a moderator in nuclear reactors where it can absorb the fast-moving neutrons and thus bring the control to the nuclear fission reactions. It is also used in conductive ink for screen printing. This is all about the graphite. Now we'll be discussing for fullerene. Fullerene was discovered by Kroto and Smalley. It is also an allotrope of carbon. The other name for fullerene is also Buckminster fullerene or buckyball, as it looks like a buckyball, so it is given the name as buckyball. And it is called as Buckminster fullerene because the structure of the fullerene resembles to the dome-like structure which was made by an architect, Buckminster Fuller. So it is also having a name of Buckminster fullerene. Fullerene exists as in different forms like C60, C70, C80. The smallest form of fullerene is C20. Here we will be discussing about the C60 fullerene, which is most stable and widely used member of fullerene family. Now we'll be discussing the structure of the fullerene, and we're taking an example of C60 fullerene because it is widely used. C60 fullerene is made up of 60 carbon atoms. Here each carbon atom is sp2 hybridized, similarly like graphite. When these 60 carbon atoms are combined together, they form a ball-like structure in which the shapes are pentagons and hexagons. These two faces are counted as there are 12 pentagons and 20 hexagons. To make sure no two pentagons share or touch each other, and each pentagon is surrounded only by hexagons. The diameter of C60 molecule is 7 angstrom. It is also having the geometry of truncated icosahedron or geodesic dome. The carbon-carbon double bond present in C60 carbon atom, their count is 30. The C60 carbon atom is having 60 vertices and 32 faces. Now, the bond length between the carbon atom existing in the C60 fullerene is carbon-carbon single bond is having a bond length of 1.45 angstrom, and the carbon-carbon double bond is having the bond length of 1.38 angstrom. Fullerene is having a density of 1.65 gram per centimeter cube. This is the basic structure of the fullerene. Here, pentagons are arranged. Here, the pentagon is arranged in a center and they are surrounded by the hexagons. Now, fullerene is also called as truncated icosahedron. Why it is called as truncated icosahedron? This structure is of icosahedron, and in this, the corners They are having 12 corners, 20 triangular faces, and 30 edges. When this icosahedron is truncated or snipped off from each corners like this, and there a pentagon is pasted, when this is done at all the vertices of icosahedron, when the corners are truncated and a pentagon is pasted, it forms a ball-like structure, or it forms a fullerene structure, which is called as truncated icosahedron. Now, this truncated icosahedron is having, similarly, it is having 60 corners, 90 edges, 12 pentagons, and 20 hexagons. Preparation of fullerene. It is prepared by arc discharge method, where the graphite rods are kept in an inert atmosphere at a pressure of 0.05 to 1 atm, and an electric arc is sparked between the two graphite electrodes. When these two graphite electrodes are sparked by an electric arc, it evaporates and forms soot. This soot is a mixture of fullerenes, and it contains around 5 to 15% of fullerene. Further, this mixture is sublimed. Sublimation is done, and this fullerene mixture is separated out by using chromatographic technique, where alumina and hexane is used, and we take out C60 carbon atom, C60 fullerene from this mixture. The properties of fullerene. The C60 molecule exists as a discrete molecule. It is mustard colored, and when it is applied and the thickness is increased, it changes its colors from brown to black. It is very tough and thermally stable, and it can be sublimed at 600 degrees centigrade under vacuum. When it is reacted with benzene, it gives a deep magenta color. One of the important properties of fullerene is also that it can lose its volume up to 30%, and there is no damage to the carbon cage-like structure. It is also possible to trap some ions inside fullerene cage, or attached some functional molecules to fullerenes from outside. Properties of fullerenes further. C60 is electrically insulating. C60 pure form is electrically insulating, but when it is doped with alkali or alkaline earth metal, then it shows a superconductivity. Again, when this C60 fullerene is reacted with organic donor, for example, dimethyl aminoethylene, it shows ferromagnetic properties. Fullerene shows variation in behavior and structure when the temperature is changed. Like at high temperature, fullerene C60 can be converted to fullerene C70. Whenever the temperature is raised, the attack is on the pentagon sides, because pentagons are more strained than hexagons in fullerene structure. Uses applications of graphite. As fullerene forms conductor when mixed with alkali metals, it can be used as conductor. Since fullerene is having a hollow cage-like structure, it can be used for absorbing gases. Fullerene is having a spherical structure, and it can be used as lubricant. It can be used as soft ferromagnets. Having powerful antioxidant properties, so it is used in health and personal cares. C60 derivatives act as potential inhibitors to HIV. And the other uses of fullerenes are, they can be used in cosmetic related materials, biomedical applications, electronic and microelectronic devices, non-linear optical devices, carbon nanotubes, and these carbon nanotubes are used in fabrics and fibers. These are some of the references which I have considered while preparing this lecture video. Thank you all.